Hi, I'm Sam Falcone, and I'm a biology student at Westfield State University. This summer, I've been conducting research through the Student Summer Research Fellow Program. My research focuses on a fish called the chain pickerel, so I'm going to go ahead and share my research with you and let you know what I've been up to this summer. So prey processing is the process by which animals manipulate and physically break down their prey after they capture it to make it easier to eat. This is especially important if the prey is large, hard, or tough. Examples of prey processing methods can include cutting, grinding, and chewing, and you may also notice that a large portion of the animals you see here are using forelimbs to maintain a grasp on their prey. So forelimbs allow animals to hold onto their prey while they use other tools they have, like teeth, to break it down even more and then push it into their mouth. This also helps them to tear their food into smaller pieces that are easier to chew and swallow, and it's especially helpful if the prey is still alive while it's being processed by the predator, since it can't get away as easily. However, if animals are having to process prey, especially live prey, but lack forelimbs to hold onto it, what do? So here I have two examples. The one on the left is Amore eel. So Amore eels have a second set of jaws called pharyngeal jaws that sit behind their oral cavity towards their throat. Once they have successfully captured their prey and are holding onto it with their oral jaws, the second set of jaws will extend forward into their mouth, grab onto the prey item, and then drag it down into their throat. Snakes also have a mechanism that allows them to process their prey through a behavior called the Pterygoid Walk, which you can see on the right. Snakes can move the left and right halves of their upper and lower jaws independently of one another, and this allows snakes to move one side of the jaw forward while the other side bites down to walk their jaws along the body of their prey, slowly dragging it further and further into their oral cavity and down their throat. So both of these mechanisms are examples of ways that animals can process prey in the absence of forelimbs. Fish are another example. So here you can see a fish called a tigerfish using a method called suction feeding to capture and process their prey. So you can see that the tigerfish is rapidly expanding and changing the shape of its mouth to generate suction and suck water and eventually the prey into its mouth. Then the tigerfish will quickly close its jaws to stop the flow of water into its mouth and stop generating suction now that the prey has been captured and there's no longer a need for that. However, if a fish isn't an efficient suction feeder like the one you're seeing here, they have to develop a different technique to process their prey. So this is where chain pickerel come in. Chain pickerel are able to generate some suction, however, they aren't very good at it and they aren't able to generate enough to really maintain a grasp on their prey. So they have had to develop a different mechanism to do that. That mechanism you can see being displayed here. So pickerel will forcefully shake their head and gradually move their jaws closer and closer to the head of their prey. And then once they reach the head of their prey, they will swallow it headfirst down their throat. So the predator, the pickerel, appears to be using a mobile clamping mechanism that allows them to hold onto and let go of their prey at the same time. How this mechanism is working remains largely unknown, so this is what we have set out to really understand through our research, just how it's functioning overall. Prior to the summer, we have worked on looking at the bones of the upper and lower jaw to see how they're moving and allowing for this behavior. So I'll give you a little information on what we found with that. So during this study, bass were used in comparison to the chain pickerel, and this is because they live in the same habitat, but they possess very different mechanisms for processing their prey. Bass are very proficient suction feeders, and whereas pickerel are designed more for maintaining that strong grip on their prey. So the most noteworthy finding that we found from looking at the bones of chain pickerel and bass is that pickerel have this bone in their upper jaw called pterygoids that we believe is contributing heavily to the ability of pickerel to hold on to prey items as they move their jaw along the body of the prey. And these bones also have a large amount of teeth on them, which is also very important. So as you can see here, when that bone rotates, it allows the position of the teeth associated with it to change position dramatically. Interestingly, there's no direct muscle connection to the pterygoids, meaning that they aren't being directly controlled. So this has led us to turn our attention to the muscles of the trunk and skull to figure out how they might be contributing to the movement of this bone as well as the overall mechanism. So an important set of muscles we were able to identify that may be contributing are the adductor muscles. So these muscles help to close the jaw and therefore could play a very large role in the ability of pickerel to close their mouth following prey capture, as well as maintaining a grip on their prey during processing. So we decided to bring the bass back and compare the adductor muscles of bass to the adductor muscles of pickerel. So bass, we believe, are better designed for the rapid closure of their jaws to cease the generation of suction following prey capture, whereas these muscles in pickerel are going to be better designed for biting and maintaining a strong grasp on their prey. As you can see in this diagram, both fish possess two major segments of these muscles. However, each segment looks slightly different from the bass to the pickerel. In each of these species, we measured and collected data on three major parts of each adductor muscle, the first being muscle fibers, the second being aponeurosis, and these are large tendon-like sheets that serve as an attachment point for the muscle fibers. And finally, we collected data on the tendons attached to these muscles. So tendons are important because they store and release a large amount of energy called elastic energy that aids in the overall conservation of energy by reducing the amount of work that the attached muscle has to do to produce a given movement. So this also aids in the fatigue resistance of that muscle. So we collected data through measuring fiber lengths and tendon lengths with calipers, and we also took the masses of fibers, aponeurosis, and tendons. We also collected photos and videos to document the arrangement of each fiber on each muscle at different degrees of jaw closure. So these are going to be analyzed using some computer software to give us a better idea of how each muscle is specifically designed and how it is functioning. So we're going to be taking this data and using the equations you see here to analyze it. So all of the calculations that we get from these equations will help us to quantify each muscle's architecture and will ultimately give us a better idea of what each muscle is optimally designed for. So we have been able to hypothesize a few things we think we'll find once we have analyzed the data. So we've hypothesized that the architecture of the adductor muscles of pickerel are going to be organized to generate greater maximum forces than those of the bass. So the muscles and tendons of pickerel, we also have hypothesized, are better designed for the storage and release of elastic energy, which would be more energy efficient, whereas in bass, they'll be better suited for direct force transfer to the jaws so that they can be closed rapidly. So understanding how these muscles work within the complex and taking what we have learned previously about this mechanism that pickerel display, we will be able to better understand how the apparatus is functioning as a whole, and this will also help us get a better idea of potential applications of this mechanism to tools like climbing tools potentially. So since this is a ratcheting behavior that pickerel are performing, it could be used to hold onto and let go of something at the same time, which could be very useful. So performing this research over the summer has really allowed this project to grow and expand, and we have learned a lot in the process. I look forward to continuing this research. I also just want to take a second to thank the other SSuRF fellows and faculty members, as well as Dr. Jarvinen and Dr. Ramsey. Thank you for watching.